So this one is the principles of projectile motion, and that's anytime that you are going to be launching something. So assume air resistance is 0. That is your friend because that means you do not need to do a calculation for the air resistance. So if the arrow is going this way, you can say the force pushing back from the air is 0. So it's one less set of calculations. But do write it every time. Air resistance is 0. Assume air resistance is 0, especially if you're planning to go on and take AP Physics later on or to take it in college. Because if you don't say that, then they will assume that you did the whole problem wrong. Okay. In fact, for my physics exam for becoming a physics teacher, I did not have time to calculate in the air resistance. So I said, I'm assuming air resistance is 0. So I'm just going to give you an estimate, and this is what I would do. And I got credit that way. And then for year 1 physics, it's never air resistance. So they might have just forgotten to put in assume air resistance is 0. I have no idea, but all I know is I still made it. So Galileo and free fall, it's the same exact thing here. Gravity is the only force. So it does not matter if you have a bowling ball or a feather, they are going to hit the ground at the same time. Okay. If we are launching a arrow this direction and we are dropping an arrow, so you have 2 different ones, okay? This arrow is going to start to slowly be pulled down by gravity. Guess what? Because of no air resistance, they hit the ground at the same time. So it doesn't matter different mass or different horizontal velocity. It does not matter, hitting the ground at the same time. Yep, and you just got to keep telling yourself that multiple times. Okay, so what forces act on the projectile? We're not counting the initial releasing the hammer on the gun or your hands on the basketball. After it's already moving, what forces are changing? And there's only one in year 1 physics because there's no air resistance. So it's gravity. And gravity is acting down the whole time. Notice all those arrows are the same length because gravity is constant, 9.8 meters per second squared. And really, I should say, we are going to assume gravity is constant. So when we're doing this one, gravity is going down, so negative g. So get in the habit. You didn't necessarily need it in module 1 because they kind of balanced each other out. But now most of the time when you're going down, just make sure gravity is also going down. So it's going to be negative. Okay. Velocity component in the y direction. Y means the vertical direction. So if I launch a projectile at any angle theta, remember this guy is theta, the little angle there, I'm launching it that way. I am going to have a y component of the velocity and I'm going to have an x component. So this slide is only talking about the y component. We launched it, so it's going to have a big launch up. But what's pulling it down? Gravity is pulling it down. So by the time we get to point B, it's going to have a smaller vertical velocity. And we get here, tiny velocity going up, and right an instant after, a tiny velocity going down. Oh yeah, we learned that too, right? Because when we get to that max height, that is when the velocity of the y is 0. That's where it's changing places. And then we're going to come back down and gravity is pulling it down. What other weird things can we see on this? B and C, their magnitude of B is the same as the magnitude of C. They are just going in opposite directions. So B is equal to the negative of C if we're going to talk about the vector version, because the vector, we have a direction. Okay? The magnitude, B equals C. The number is going to be the same. Okay? And velocity, Y. So at the start and the end, equal and opposite. So that's how those Y forces are going to be going. And So when we're comparing, this has a velocity of 0. So both B and C are larger. And you're going, but one's negative. Remember, negative is only the direction. So both B and C have a larger speed than velocity. Why? Because speed is a scalar, no direction. It's a weird thing. By the end of the year, it will sink in about the weird thing about direction. Okay. At maximum height, the velocity in the y is 0 because what goes up must come down. But this one also pulls in and gives you those components. So if I have a force U, that's the resultant force, it would also be U times cosine theta for the X component or the horizontal component, or U sine theta for the vertical component or the Y component. So that is what you can see at each of those spots. Now, horizontal velocity, if I launch the arrow at 10 meters per second and there's no air resistance, 5 seconds later, it's at 10 meters per second. 20 seconds later, it's at 10 meters per second. When does that horizontal velocity change? When it hits the ground. So if the arrow hits the ground between these first two measurements, then yes, you would have a different horizontal velocity, because once it hits the ground, it would be 0. Okay. But if it hasn't hit the ground yet, your horizontal velocity is constant. Horizontal velocity is constant because we have no air resistance. So you can use your V average, your favorite little V average distance over time for the horizontal or the X. So that's how I'm going to change that formula that you can add, onto your page. Velocity in the X is equal to the distance in the X divided by the time, providing that air resistance is 0 and we were working with a projectile. At maximum height, the time is the half of total. So that's your important thing here. So if you find the time for going up, then you can double it for the total time. What goes up must come down. Doesn't matter what angle it started at, because you're getting a parabola here. So even if it's a steeper angle, it is still going to be half the time before you got to max height and half the time when you get after. Half plus half gives you the whole time. Projectile versus free fall. I said this at the beginning, but I'm going to say it again with a picture. Okay, if I drop something here and there's no air resistance, it's going to get faster and faster as it goes down. If I have a horizontal velocity, so a velocity initial in the X or VI in the X, it is still right here. It's VI in the X is still the same as the initial velocity. So VIX is equal to VX. Same way, because it's an average velocity or a constant velocity in the X. But it is going to be accelerating in the down direction. Why? Because it's accelerating from gravity. Both the left and right are accelerating the same from gravity because no air resistance. So these guys are going to hit the ground at the same time. So that is your clue 1 for 2.2, because it's going to help you figure out lots of information. You can find the time from the free fall if you have the distance or the height. And then you can use the time on here to help you find the range. So that is why it's important to know that. And that means the distance in the X or the range. Yeah. And there's some equations right there that you could use just like that if you wanted. You can always add equations to your page. Distance in the X equals velocity in the X times time, and that is your range. So that's a big one that you're going to use. and the distance in the y is the height. So it's the velocity initial in the y direction times t plus 1/2 at squared. What is that a? Negative 9.8. What is my velocity initial? A lot of times it's going to be 0, but not always. Read carefully. If they said we push the ball down, then it does not have a velocity of 0. But if they say we drop the ball, then you can assume that the velocity initial equals 0. Just read carefully. A lot of this unit is reading carefully, especially since it's going to say horizontal, vertical, distance, velocity. Make sure you're answering what you think you're going to answer. Right. Galileo drops a feather at the same time and height that his daughter, Maria Celeste, throws a baseball horizontally at 10 meters per second from the top of the Leaning Tower of Pisa. Assume no air resistance. So you're going to write that there. We know the horizontal initial velocity in the x direction is 10 meters per second. We know the velocity initial in the y direction is 0 because we're not pushing it down. We know the height is 186. Oh, that's a feat. We got to do a change, don't we? 186 over 1 from 3.28 feet to meters. So make sure you do that conversion there to convert to meters. Make sure your answers are always going to be in the SI units unless it doesn't tell you. Okay, it might say keep answering feet, and that time you do not have to convert. All right, so then we have the height or the distance here. We have the velocity initial in the y. We have the velocity initial in the x. When does the baseball hit the ground? So we are looking for a time. So again, we're going to look at those same equations that we had before. V final equals V initial plus AT. V final squared equals V initial squared plus 2AD. Distance equals velocity initial times time plus 1/2 AT squared. Same ones. It's just that they've been reworked a little bit so that they can say in the X and Y to help you out. So distance in the Y direction is the velocity initial in the Y times the time plus 1/2 times the acceleration in the Y times time squared. So that's the part. Is that going to help us solve it? Nope. Why not? Because we don't know our distance in the y. Oh, distance in the y. I can't count. Distance in the y, we do know. We solved it right here. I was thinking I did x the first time. Okay, so what is our distance in our y? It would be 186 divided by 3.28. So 56.71 is our distance in the y, or our height, is equal to VI in the y, okay? She threw a baseball at 10 horizontally, but it has 0 for its initial velocity. So 0, and then 0 times t, so we know that's going to end up being t, plus 1/2. Acceleration, I'm going down with gravity, negative 9.8 t squared. So then when we solve this guy, we are going to actually, we're going down in distance too. So we'd have a negative in that case. So if you got to the end of here and said, wait a second, I have t squared equals a negative number, that's just to remind you that that's what was happening. 56.71 divided by the quantity of 0.5 times 9.8. And that gives me a t squared, if you're doing it at home, 11.57. And then we take the square root of that, and we get a time of equal to 3.40 seconds. So that is how you would work through that problem. 0 times t is t. That's why I didn't have to put that in the next part of the equation. Okay. And there's the little things. So there's the equation and the acceleration due to gravity to help you out. There's the conversion there again. There's the answer if you want to try it. This is a good one to screenshot and then try it later on. Okay. What is the horizontal velocity of the ball at 3.3 seconds? So right before it hits the ground, what is the horizontal velocity? So once it hits the ground and skids to a stop, it would be velocity is 0 because it's a stop. And so velocity in the x would be 0, velocity in the y would be 0. But what is the velocity in the y right before it hits? Remember, the velocity in the y is constant. So it's going to be 10 meters per second because we don't have air resistance slowing it down in the y direction. We don't have gravity speeding it up. Why? Gravity only works in the x direction. God, I said y again. This is velocity in the x direction is 10 meters per second because the x is constant. It's always 10 meters per second because there is nothing pushing back. There's no air resistance. Velocity in the y is going to be speeding up. Why? Because acceleration is pulling you down. So again, horizontal velocity right before it hits is still the same horizontal velocity as before, 10 meters per second. Okay. How far away is the baseball from the tower at 2 seconds? Right, so we want to know, not the full range. So we can't use the full range here. We want to know what the distance in the x is. So we look at our equations again. Distance in the x, velocity initial times time, plus 1/2 at squared. Okay, how far away is the baseball from the tower? How far away? That's how we know it's a distance in the x, velocity initial in the x times time, plus 1/2 acceleration in the x times the time squared. The times are the same regardless if you're looking at the x component or the y component. The times are the same regardless if you're looking at the horizontal or vertical. So when we're looking at it, we're going to put in 2 seconds there. We don't know the distance in the x. We know the velocity initial is 10. We're 2 seconds away. What is the acceleration in the x? Is it getting faster in the x direction? No, velocity is constant, so acceleration is 0. Distance in the x is equal to 20 plus 0, or just 20 meters. Read super carefully. Sometimes it wants you how far away from the tower or how close it is to the ground. So really read quite carefully when you do these quizzes. Where is the feather at 2 seconds? Which one's the feather? Go back and read. That's the one that was dropped. So at 2 seconds, it's going to be dropping 2 seconds down. It's not going further away. We need to know how far along on the drop is it. Okay. So what do we have? We have a velocity initial equal to 0. And we have a time of 2 seconds. Velocity final equals velocity initial plus acceleration times time. We have velocity initial. What's our acceleration? Is -g, and we have a time. So this one is great if you want to find velocity final, but it didn't say how fast is the feather going at 2 seconds. So let me try a different one. Distance is equal to velocity initial times time plus 1/2 at squared. We know velocity initial. We know our time is 2 seconds. We know our acceleration and 2. So this one's going to happen. Velocity initial is 0. So 0 times 2 is 0 plus 1/2 times -9.8 times 2 squared. And so we are going to get, we are going down 19.6 meters from the top. So where is the feather? Make sure you read carefully on the problem. We've gone 19.6 meters down. But if they want to know how high off the ground it is, you would have to take the total height minus 19.6. So read carefully. It's fallen 19.6 meters. Okay, 19.6 down, or 37.1 from the bottom. So read the question really carefully. And yep, you could use some logic to really guess if you're doing okay. We know the feathers at 2 seconds. Okay, it started at 0 velocity. So after the first velocity, it increased by 9.8. After the second second, it did 9.8 times 2. So you could kind of logic it out that way, but it does increase your chance of errors. Just use the logic to double check. Okay, I got a close answer and I'm probably good. Okay. If the height of the cliff is doubled, what happens to the range? So normally the height is 1/2 GT squared. Okay. And the new one is going to have 2h in there. Okay. And so when we consolidate like terms, what's the difference? This guy has a 2 to the 0.5 as opposed to a 1 to the 0.5. So it's going to be 2 to the 0.5 bigger than the other guys. If you're like, whoa, that made no sense to me, then substitute in 9.8 for the gravity, substitute in 10 for the height. This guy has double the height, so you put 20 in and 9.8 in. Solve the one on the left, solve the right on the right, and then compare their answers. And that's it for today.